we often will use sample statistics as estimators for population parameters. But in order to quantify how good of an estimator it is, we really need to have an understanding of the underlying distribution of that statistic. So let's look at how we can simulate and understand distributions of statistics. We're going to have a lot of distributions referred to in this video, so I want to lay out the different ones and give you some analogies. We'll talk about the population distribution. That's the underlying distribution of whatever variable we're interested in analyzing. For some toy data we'll be working with in a minute, we're going to be looking at the time of delayed United flights. We have some data over a set time interval, and we'll look at whether or not the flight actually left before or after its scheduled time. This is usually not known, right? But in our example here today, we'll start with known population distribution and show you how we can then go backwards without knowing it to try to make some inferences. Ideally, we would want to know some characteristics of this distribution. For example, like what's the average time of delay for United flights? Or in this case, because it's skewed, we'd probably use median as a better summarizer. And so here, in this case, the population median is 2 minutes. Again, this is a fixed value. This is a number, and this is usually not what we know. It's usually what we're trying to infer. Okay, what we usually have access to is just a sample of our original population. And so if you want to imagine, I'm going to randomly sample 100 different United flights from this population distribution, and then I'm going to plot the distribution of my sample. Here's one such plot. This is the distribution of 100 randomly sampled times. And you can see this distribution shape is pretty close to the population distribution shape. That's generally the case as long as your sample size is large enough. But if I were to repeat this process, I'm going to get a slightly different sample. And again, here. So these samples themselves can vary. Now, if I want to use the sample to estimate a population parameter, in this case, I could use this first sample to try to estimate the median of the population by using the sample median. In this first case, it turns out the sample median is 3, pretty close to the actual population median. In the second case, it's also 3. Third case, it's 2. And so I want you to realize that this sample median itself is a random variable. And so I can now take these outputs, 3, 3, 2, and start to aggregate them into their own distribution. If I were to then do this a ton of times, like say I repeat this 1,000 times. Again, this is all a theoretical exercise because in reality, if I had the time and money to go resample this population 1,000 times, I likely would just spend all my time getting the original distribution. It doesn't really make sense to do this. It's not usually practical to resample and resample and resample. And so we will talk about some workarounds for the real world scenario of this. But first we need to see what would happen in a theoretical best case scenario. So if I were to do this process and I keep getting 10,000 different samples or 1,000 different samples, calculate the medians for all those samples, here is the distribution of the sample medians. And so I can see that here was the actual population median, which was 2. I'm getting values that are around 2. They're not perfectly centered around 2 in this simulation, but then I get a sense of the spread also. So I'm not likely to get a sample median of 10, right? And I'm going to rarely get 8, but it's possible I get a sample median of 6, even though the real population median is 2. So we're going to use the spread of this distribution, as well as where it's centered, to help us quantify how confident we are in our estimates when using sample median to estimate the population median. I want to have us visualize this a little bit more before we jump into more of the theory. So let's go to this website here and look at a quick demo. Now let's explore with this demo to get a better feel for the terminology and the things we're working with in this lesson. And I highly recommend you just play around with this demo. I really like this because it's flexible. You can totally make up your own parent population distribution, make it look as strange as you want. What I want us to understand is this is a way of visualizing those three different distributions I had on our slide. The top one is our parent population. Here is going to be the distribution from a sample, and we'll get to decide the size of the sample. We'll set 10 here, 25 here, and then you're going to pick a statistic. I'm just going to pick the median for both of these since we've been talking about medians. Let's visualize. Let's actually do it just for the first one here. We're going to do a size 10. Here is taking a sample of 10 from my original distribution and then calculating the statistic from that sample. So the statistic of interest was the median. Here was the median. Now notice, like the median for my original distribution was 18, right? And my median here that I have is not 18. It's not that far off, but it's lower. And so I'm going to get a different value depending on each sample I take. If this was like the real world and I only had one sample and I wanted to use that median as a good estimator for my population median, I would need to have some more understanding of like the spread and the center of this distribution. So that's what we're going to do. We're going to do it again. We're going to try to build up this pink distribution to get a, we'll see that one was way different. I'm getting a pretty big spread here, but let's do it again. Now, I'm only doing this for you manually, like 3 or 4 times, but we could start to speed up this process. I'm doing this in groups of 5. So when I do this, you're missing this animation that's happening each time, right? Each time I'm taking a sample of size 10 to get my new pink spot. Okay, so we're going to keep doing this, and then if you want to jump to doing this a lot of times, I can hit 10,000 or 100,000. Okay, so this is interesting because this is the distribution of my sample statistic. On average, if we want to look at the mean of this, so it's in blue, on average, the mean, it's right around 16.37. The actual median up here that I'd like to predict, right, was 18. So if you notice, the center or the expected value of this, not the center, but the expected value here of this is 16.37. It's a little bit off from the actual parameter I'm trying to predict. When that happens, we call this statistic a biased estimator. It's not bad, but we notice that the expected value of this is not exactly the same as the value we wanted to get. It's a small bias here, right? I want to get 18. My expected value is 16.3. But that's important to understand, right? Do we have a biased or unbiased estimator? Also, we can look at the spread, right? So I can see like, I might get sample medians anywhere in this range. It's a pretty wide range. How good or confident can I be in my estimate given how wide this distribution is? I can't be very confident. So what if I were to increase my sample size? So let's look at that here. Let's do the median here. We're going to redo this process. I'm only going to do the animation once because it's going to take a bit of time. So here it's doing 10 and getting me a median from those 10. And now it's going to do 25 and get me a median from these 25. Okay, so one thing I want you to notice is when I do 25, the distribution here should look better than just doing 10. And by better, I mean it should be more representative of the parent population. 25 is still a very small sample size. So ideally, we're going to be doing things like 100 or 200. We'll talk about what sample size we need. But just for the purpose of the demo here, we have a small number so you can see it quick enough. All right, let's do this in groups of 5 and start to see. And I want you to guess before I finish this how the spreads of these are going to compare. So do you think they're going to have the same spread if I use n equals 10 versus 25? Or do you think one of them will have a different spread, like smaller or larger, and which one? Okay, so if I keep going, go to 10,000, 100,000. Aha! Okay, so we have a smaller spread. And again, I'm measuring spread. You can think of it as being measured by your standard deviation. It's smaller in this. It's 5.26 instead of 6.5 when I used a larger sample size. That's helpful because I'm less likely to be off with my estimate here as I am here. It's possible I get a very wrong estimate for my population median if I use my sample median in this one. But I still have an interesting like this bimodal thing happening, and the mean of the second one, 16.6, is still not exactly equal to the value I'm trying to actually estimate. So I'm still getting a biased estimate here, but not that bad. These are the types of questions that I want to be able to answer so that I can mathematically quantify the quality of using a sample statistic to estimate a population parameter. Now let's look what happens to the sampling distribution if we change the statistic. So here I had 10. I'm going to just up this to 25. And instead of doing the median down here, let's actually look at the mean. We could look at any other statistic here. I'm going to start to do this again and then jump to, and so you'll notice these distributions look very different, not only in their spread, but in their shape. This one's much more bell-curved, whereas this one is got this bimodal activity happening here. And it could be a question as to like, maybe that's just an artifact of this parent population. So let's try, I don't know, let's do like this skew. I'll clear my lower. Let's do median and mean again. And we're going to start visualizing what's happening. Aha. Okay, and so here I can see my distribution of medians versus distribution of means. You notice they're shifted. They're centered at different spots, which is good from an intuition standpoint because this distribution of medians is trying to measure is the distribution of this sample median, and my actual population median is 7. So I would like this ideally to be centered closer to 7, whereas my distribution of means is trying to approximate the actual population mean of 9.69, so I'd expect it to hopefully be centered closer to that actual population mean. And I can actually see that's very true here. This is centered at 9.7 when the actual population is 9.69. That's a great property. So some of the things we're noticing is that the shapes of the distributions can change depending on the parent population and sometimes depending on the statistic we're using. And their spreads can change, again, depending on the statistic, as well as depending on the number of samples we use. And their centers can change depending on the statistic. So feel free to play around with this some more. If I wanted to do something like range, look at that one, right? I get a very different sampling distribution of ranges here. And this is trying to basically estimate the range, which is the difference between the largest and the smallest values here, which would be 32. So these are going to be important characteristics, is really understanding what does the distribution of a given statistic look like? How does it change with sample size? Is it centered, or is its expected value equal to the population parameter I'm trying to estimate? And how big is its spread? Those are all questions we want to answer to help us quantify how good our estimates are. So we just looked at a great demo online, but let's look at how we can code this same idea so that we can simulate the sampling distribution of a statistic of interest. So this is in the central limit theorem folder. Go to sampling distributions. We're going to recreate those images that I had on the slides using the United data. So here I'm loading it in. This is all of their flights for a given 3 months in 2015. And then look at how you can take a random sample. So DataFrame has a built-in method called .sample. The default is without replacement, but we would like to do this with replacement. So we're going to set replace equal to true. And whatever number you put in here will be the number of rows that it randomly samples. So if I do it again, I'm going to get a different number of rows, or get a different set of rows, excuse me. So if we want to go plot the original population distribution And then we can calculate some parameters of the population. So we saw that the median was 2. We could also look, say, at the min or the max or the mean. These are all different parameters of the population. Again, in the real world, we don't usually have access to that full population data. If we did, we'd be done, right? Whatever we wanted to answer about this data, we have everything we need. We can calculate probabilities, we can calculate parameters, we're done. In reality, we only have access to a sample. So that's, for example, here's one such sample. It's going to look pretty similar to the distribution of the population. But if I run it again, I'm going to get a different sample. And run it again, I'm going to get a different sample. And now I can use these samples to calculate statistics and to get a sense of what the distribution of the statistic would be. So if I want to do the sampling distribution of the sample mean, we can see my medians from the first sample was 5, second sample was 3. Oh, I didn't rerun it. Let's just rerun that. Okay, rerun this one. So I got 5, I got 2.5, I got 2, and now I can put this together in a function. So this is going to take a random sample of size 5, or whatever size I want. Let's do size 100, calculate the sample median. I do it again, I get a different one. And so what I'm going to do is repeat this process. Let's do it 10,000 times to get my sampling distribution of the sample median. And so here is what that distribution looks like. I get a good sense of the spread. If I would like to see the expected value of this, I can take the mean, which is, right, giving me 2.6. And so again, I can see knowing this information, right, about this distribution helps me then take a sample median from a given sample and provide some good quantification about how confident I am, how close it really is to the true population parameter when I don't actually know the true population parameter. Here I do know that it's 2. So we're cheating, but in reality, we usually only just have some value from this distribution. Now, we were looking at medians, and then we switched over to thinking about what happens with means. So let's also simulate the mean, the distribution of the sample mean. And so the only thing that changes is that I now calculate a new statistic on my sample. I get my new distribution. Aha, and so notice again, this one's looking bell-shaped. We're going to see that's been a common theme. Every time we do the sampling distribution of the sample mean, we get something bell-shaped. We'll see if that was just a coincidence. Let's see where this one's centered. 16.67. If you recall, here's the actual population parameter. Aha, 16.65. So this is interesting. We'll see if this was just a coincidence or not in our next slide. But the expected value, or the average of my sample means, is basically almost exactly the actual population parameter I'm interested in estimating. That's helpful information as well. So let's pop back over to the slides and put some theory behind what we're observing here. So again, we've established that statistics are random variables. So the sample mean is a random variable. We could, again, start with some random population distribution. Here's one that I used from that online simulation. And we could ask, what is the distribution? Let me move that. What is the distribution of the sample mean? What does this look like? And in particular, I could say not only is what is the shape of it, but what is its expected value? What's the variance? And what's the standard deviation? Statisticians have a fancy name when we talk about the standard deviation of a statistic. In particular, we call it the standard error of the statistic. And we'll see why, because we're going to use that value to help us come up with error bars around our estimates in some future videos. Question 1, I'm going to be continued. We're going to answer in the next video. But question 2, 3, and 4 we'll actually be able to answer here, just based on our understanding of expected value and variance. So what is the expected value of the sample mean? Well, I'm going to take the expected value of this, so the expected value of 1 over n times the sum of x sub I, and we know from properties of the expected value that the expected value of a sum is equal to the sum of the expected values. So that's what I've done here. I've moved it inside. And then we know the expected value of each of these, well, is the same as the expected value of my underlying distribution. Let's say that that is mu. So I have n of those mu's. So at the end of the day, the expected value of my sample mean is actually the population mean. This is great. This is what's called an unbiased estimator, using the sample mean to estimate the population mean, because the expected value of this estimator exactly equals what we're trying to estimate. It's called unbiased. That's a great property. We can also talk about the variance. So now I'm going to do the variance of this sample mean. Fun fact is, because these are IID, the covariance of these are going to be 0. And so the variance of the sums equals the sum of the variances, which is therefore going to simplify to be the variance of the original population, right, sigma squared, divided by n. Which means that the standard error, or the standard deviation of the sample mean, is just the square root of that variance, which ends up being the standard deviation of the population. So I will usually write this as sigma sub pop, just to remind us, divided by square root of n. So one of the things we can take away from this, and again, what was n? It was our sample size, right? And so I can see that if I would like to get a sampling distribution that is at a smaller spread, I'm going to need to take a larger sample size. In the next video, we're actually going to answer part 1 to say, okay, well, we now know the center and we know the spread, but what's the shape of the distribution of the sample mean?